Hello, my dear warriors. Welcome aboard to the next session of your Fastrack series. Fastrack series is aimed to cover all the important topics for your JEE examination or even other such examinations in a very small amount of time, in a very crisp manner. And today I'm going to discuss everything about nuclear physics, right from what a nucleus is to binding energy, radioactivity, and also the radioactive particles. So all of this with me, your physics master teacher, your navigator on this channel. And I've been training and nurturing kids just like you who are very enthusiastic to crack the JEE examination. So let's scale up your level in this fast track sessions. I hope you have subscribed to the channel, because apart from the fast track mind maps and formulas, there are also fast track problem solving sessions where previous year questions, NTA Abhyas questions, top problem questions are being solved. So make sure you stay subscribed, and if you want YouTube to recommend more such sessions, make sure you smash the like button, because that's how the algorithm works. And show your immense love and support in the comments as well as in the likes. Thank you very much for smashing it. Let's begin with the class. So nucleus is inside the atom. Atoms are basically the teeny mini particles which make up any matter or bodies around you. Nucleus is very heavy and it is the dense part of that atom. It's located somewhere close to the center, and it is made up of two smaller particles called as protons and neutrons. Together, these protons and neutrons are called as nucleons. Nucleus is positively charged only because of the protons present inside it. The neutrons which are there are neutrally charged, although they have very similar mass as compared to the proton. The electrons keep revolving around the nucleus, which is centrally located in an atom. The neutrons and protons together, like I've told you, they are called as nucleons. The mass of the neutron is close to 1.67 10 to the power minus 27 kg, quite heavier than an electron whose mass is in the order of 10 to the power minus 31 kg. Mass of a proton, you can see, is 1.6726, slightly less than that of a neutron, and to the power 10 to the power minus 27 kg. Going ahead, the way in which you represent any element depends on what is there inside the nucleus. The nucleus decides the chemical properties of any element. So, talking about X, X is basically the symbol of the atom. It could be hydrogen, helium, oxygen, whatever it is. Z is the number of protons, which is also called as the atomic number, which also decides the chemical properties. Then you have the atomic mass number of that particular element, which is denoted by the symbol A, and A is the sum of Z, which is protons, and also the number of neutrons. So protons and neutrons together give you the atomic mass number, and this is how you represent it. The element symbol will be over here, the atomic mass number as a superscript, and the atomic number will be there as a subscript, right? So that's how you represent any element. The next important thing is regarding how you show these masses, because we know the masses of protons or neutrons are very teeny mini, so we use a new unit called as the atomic mass unit, which is 1/12 the weight of a C12 atom, and that comes very close to 1.6603 10 to the power minus 27 kg. And you will see that the mass of the neutron and proton are very close to this value, so you can say it is roughly equal to 1 atomic mass unit. In the exact atomic mass unit, obviously there will be a difference in the later on decimals. Now, going ahead, talking about the different comparisons and the relationships between different elements based on their atomic numbers or mass numbers or neutrons. So first thing is isotope. Isotopes have similar properties, but they have different atomic masses. Like you can see, these are the three different isotopes of hydrogen because they have different atomic mass numbers. These are three different isotopes of oxygen because even if their atomic numbers are equal, their mass numbers are different because different number of neutrons are present. Protons are the same. Then you have isobars, where you will see the atomic mass number is same, exactly opposite of this, but atomic numbers are different. So that's why you will see the elements are different. This is hydrogen, this is helium. Mass numbers are same. That means protons and neutrons, the total number is the same. The last one is the isotones, where the number of neutrons are same. like the one over here, lithium and beryllium. You can see 7 minus 3 is 4 and 8 minus 4 is also 4. So they have 4 neutrons each. So they are isotones. So that's your basically isotopes, isobars and isotones. Moving ahead now to the radius and the density of the nucleus. The size of the nucleus completely depends on the number of nuclear particles inside of it. So the radius is found to be proportional to the atomic mass number raised to 1 by 3. The constant of proportionality is R0, which has a value of 1.2 fermimeter, which is also 10 to the power minus 15 meters. So that's how small the nucleus is. Compare it with the size of the atom, which is of the size of roughly few Armstrongs. So you can see the nucleus is extremely dense and teeny-meeny. And the best part is, if you find out the volume and also divide mass with the volume, you will get the density. And best part is, the density of all the elements comes out roughly the same. It comes out independent of the atomic mass number, something that you should be aware of and also been asked in many of the competitive exams. Now you might be wondering, how do these particles which hate each other stay inside the nucleus? Like two protons, they will repel each other because of the electric forces, but in spite of that, they are very, very stable inside the nucleus. So there must be something of higher in magnitude which binds them together, and that is basically nothing but the nuclear force. So this nuclear force acts inside the nucleus, very short range, between a proton-proton, neutron-neutron, or even a neutron and a proton. They are a new kind of forces in nature, just like you have electric force, magnetic force, gravitational force. So this is a new force of a fundamental kind which acts at a very, very small distance, very short range, but much more powerful than gravitational or electric forces. They do not depend, these nuclear forces, they do not depend on masses or charges. They in fact end up depending on the spin of these particles. They do not follow the inverse square law just like the other fundamental forces of nature. They are also saturated forces, and they are basically exchange forces, meaning they act for a short distance and they suddenly vanish off after a certain distance. And these forces happen because of exchange of certain particles. That's why it is called as an exchange force. All right. And usually you will see that the nuclear forces are attractive in nature. So these are the theory things which you should know for nuclear force. You do not have any formula based questions on the nuclear force. So now you know how these particles stay together. We will talk about the mass of a nucleus and the mass of the particles making up the nucleus. For example, if I take helium nucleus, it's made of 2 protons and 2 neutrons. And if somehow I was able to compare the masses of these 2 protons with neutrons and the helium nucleus, you will see the helium nucleus is lighter than the individual particles. How does this happen? When these particles come together, there is some mass which is lost, and this mass which is lost to make up the nucleus is basically called as the mass defect. So mass defect, simply put, is nothing but the reduction in the mass which is destroyed, the mass which is lost when a nucleus is formed from the individual particles. So if Z is the number of protons into the mass of the protons plus the number of neutrons, which is also A minus Z, into mass of the neutrons, will give me the total mass of the particles minus the mass of the nucleus, which is slightly less, gives you the mass defect. This is a very, very small quantity, but it is there. Now, why does this mass defect come? Well, the answer to that is binding energy. Let's talk about it, but before that, the mass energy equivalence. Einstein said that whenever you destroy mass, energy is created, and whenever you destroy energy, mass is created. So whatever this mass is lost, it's not gone forever, it's gone into form of energy. So basically the mass which is destroyed into c square gives you the energy which is going to come out. If energy is destroyed, mass is created again by the same formula. So this is a very, very important formula which gives you how much mass equals to how much energy when created or destroyed. So the mass which is lost gets converted into something called as the binding energy. So these particles, protons and neutrons, come together. There is some loss of mass which is released in the form of binding these particles. That's why it's called as the binding energy. Alright, and this binding energy, simply put, is the mass defect. Mass defect into the c square. Now usually these mass defects, like I told you, is very small. You would not prefer to write these masses in terms of kgs. You would generally write it in terms of atomic mass unit. And when you convert it into atomic mass unit, then the answer of the energy which is released, or simply put the binding energy, comes out to be delta m in atomic mass unit into 931, where this is mega electron volt. That's a tremendous amount of energy which is created for even the teeny mini masses out there. So this is the, in fact, the reason or the working principle behind, your atom bombs, where masses get destroyed and tremendous amount of energy gets released in a short duration of time. So that's binding energy for you. Now, when these particles come together and this binding energy is released, it's a good thing, because more the binding energy released, the better it is for the stability of the atom. But that's not true completely, because what actually matters is how much binding energy is released per nuclear particle, that is binding energy per nucleon. That is the factor which decides the actual stability of the nucleus, because per nuclear particle, how much energy you release decides how stable those particles are inside the nucleus. So the binding energy per nucleon is total binding energy, which we just calculated, divided with the atomic mass number. That will give you the binding energy per nuclear particle. So delta m is mass defect into 931, that's the mega electron volt of energy released. A is the number of neutrons and protons together, so divided. That's your binding energy per nucleon which is there for every element. Now, like I said, it decides the stability. So scientists have plotted this binding energy per nucleon for different elements, right from hydrogen to the last element in the periodic table. And guess what? The graph goes up, shoots up, and then almost stabilizes but slightly lowers down for higher elements. This graph clearly tells you that these elements have high binding energy per nucleon as they are more stable. These elements are less stable. So this graph in fact tells you about the stability of all the elements in the periodic table. So every element over here would like to break down into smaller element, whereas these elements would like to combine together to become these elements which are much more stabler. Whenever these nuclear reaction happens, what happens is that there are smaller particles which might come out, and there are three major particles which you should know: alpha, beta, gamma. Alpha is nothing but doubly ionized helium nucleus. So it has just 2 protons and 2 neutrons, no electrons in it, so it has a 2e positive charge. Beta particle is nothing but an electron, sometimes also called as the negative beta particle. Beta positive is called as a positron. We will not talk about it so much, but you should know that beta positive also exists. It's just like an electron, same mass but opposite in charge. Gamma is not even actually a particle, it's not matter as such, it's a photon. So it's basically the particle of light. So gamma is actually electromagnetic radiation, or just simply put photon, because gamma particles or gamma radiation is electromagnetic radiation. It travels really fast, it hardly has any size, so it can pierce through most of the materials. Whereas alpha, being bulky and little bit bigger in size and heavier, they travel little bit slowly and they will get easily absorbed. They will not be able to pass through many sheets. Beta have slightly higher speeds than alpha, not as much as gamma, and they can pass through thin sheets but not through thick sheets of metals. Also, you should know certain important properties regarding ionization power, their atomic mass unit, etc. Alpha, obviously 2 protons, 2 neutrons, so 4 atomic mass number. Beta is an electron, hardly any mass. Gamma is not even matter, so rest mass is 0. Charge of a alpha particle is plus 2e, whereas for a beta it is nothing but negative e. For gamma it is chargeless, so it will not get deflected by electromagnetic fields. Last thing which you should know is ionizing power. Alpha particles being bulky and heavy, they have high ionizing power but low penetration. Beta, moderate ionizing power, but they can penetrate little bit better. Gamma has the least ionizing power, but they are going to pass through many layers of metals or sheets. Also, you should know what they do to the nucleus. Alpha particle reduces the atomic mass number by 4, the atomic number by 2. So the element shifts by 2 positions on the periodic table. Whereas in a beta decay, that is when an electron pops up, you will see the atomic number will increase by 1. Mass number does not change. This happens because a neutron inside this nucleus converts into a proton, so that increases the atomic number, and an electron is just thrown out. The last one is the gamma emission. In that you will see the excited nucleus comes to a lower energy state. So you will see this is excited, this is ground state, and it releases a photon. So there is no change in mass number or just atomic number. There is no change in gamma radiation. Only changes happen in alpha or beta decays. Now that you understand what nuclear reactions are all about, like I said, elements can break into smaller particles, or smaller particles can combine to become a more stable nucleus. The first one being called as fusion. Fusing means gathering things together, joining them together. So 2 or more nuclei joining together to become a much bigger nucleus is called as a fusion reaction. The one which happens in sun, or artificially you can create small suns in a nuclear reactor. Also, there is the second part, which is fission, which is breaking. So either it can be natural, maybe an unstable nucleus just breaks naturally, or you bombard a heavy nucleus with a particle and it breaks into fragments. Just like when you hit the coin on a carom board, the coin scatters all the other coins around it. So that is breaking the nucleus into smaller nucleus. That is called as fission reaction. Now each of these reactions involves some kind of mass defect and also changes in their binding energies. So because of which some energy might be released or some energy might be absorbed. The energy which is released or absorbed in a nuclear reaction, fusion or fission, is called as the Q value of the reaction. So if 2 or more nuclei combine together or split into smaller nuclei, you will see that there might be some energy which is released or energy which is absorbed. Simply put, it is nothing but the difference of the masses on the left hand side with the masses on the right hand side. So that gives you the mass difference into c square will just give you nothing but the Q value, which is the energy released or which is absorbed during that fusion or fission process. Is that clear, everyone? So keep this in mind. Whenever you write this formula for masses, you will write masses of LHS minus masses of RHS into c square. But if it is binding energy, then you write binding energy of right hand side minus binding energy of left hand side. So the formula reverses when you write in terms of binding energy, but you keep it LHS minus RHS simply when you write it in terms of masses. Alright, one other important thing. Now, like I told you, the heavy nucleus might want to split into smaller nucleus, which is fission. This fission, when it occurs naturally, without any force or without any particle being bombarded onto it, that is called as radioactive nucleus. It is said to possess this property of radioactivity, where it naturally decays into much stable nucleus. So a heavy radioactive nucleus decays by emitting alpha, beta or gamma particles, and sometimes these radioactive nuclei are very dangerous to human beings because they can cause, a lot of diseases. They can even cause cancer, and they might be very, very fatal to most of the living beings. Now there is a law which tells you how quickly this decay happens, and that law is called as the law of radioactivity, which does not depend on external factors like pressure, temperature or anything else, because it's a completely nuclear phenomena. So the law of radioactivity says that dN by dt is lambda n, where dN by dt is the rate at which the nuclei are decaying per unit time. N is the number of nuclei present at any instant. Lambda is just called as the decay constant or disintegration constant. And this completely depends on which nucleus you're talking about. For thorium, for uranium, it would be different values. So this negative sign is just telling you that the number of nuclei are reducing with time, So it's important to know that there is a negative symbol over there. Now when you integrate this with proper limits, this is the formula you get. N is the final nuclei present, N naught is the original number of radioactive nuclei present, lambda is light spread over here, decay constant, T is the time spent. So N is N naught e to the power minus lambda T is the final formula that you get using the law of radioactivity. So with this you can find how many nuclei are present after some time. Now you also have another thing called as activity, which is nothing but how many nuclei are decaying per unit time. So this term minus dN by dt, which I showed you over here, this is also just called as the activity of that particular sample. By simple substitutions, you can also see the final activity is the original activity e to the power negative lambda t, very similar formula to this one. So this formula is for number of nuclei present, whereas this formula is for the rate at which the nuclei are disintegrating. So that's for activity. The units of activity are basically generally becquerel and curie. Becquerel is very simple, it's just 1 disintegration per second, but 1 curie is 3.7 10 to the power 11 disintegrations per second. The next thing that you should know is basically the half-life of any element. So as the element decays into a much more stable compound, you will see that the number of nuclei which are present in the sample decays exponentially because the formula had e raised to negative lambda t. And after some time the sample reduces to half its original value. So that time taken to reduce to half its value is called as one half-life. After 2 half-lives, you will see half of half will be left out. So that is 1/4 of the original sample will be left. So after n half-lives, you will see n naught by 2 raised to n radioactive elements or atoms will be left out over there. Because after every half-life, half of the previous sample will be just present, the remaining half would have been decayed. This half-life is just given by the formula log of 2 to the base e, of course, divided by lambda. You can use log 2 for value as 0.693. That's the formula for half-life in terms of the decay constant. You have another thing called as the average life. So every element stays alive for some amount of time before it finally decays. So if you take the time which every nuclei stays alive, T1, T2, T3, and take the average of that, that is called as the average life. So in average life, the formula is just 1 by lambda. There is no log 2 just like over here. So the average life is just simply put 1 by the decay constant. So that was your nuclear physics. I hope you guys enjoyed and learned and revised a lot of things which you might have forgotten, and listen to this in loop in case you want to just revise this topic towards the end just before the exam as well. This chapter is definitely going to fetch you around 4 marks in most of the competitive exams. So thank you for liking, thank you for subscribing. Do let me know in the comment section how you enjoyed the session and what do you want next. Bye bye guys, this was Captain Shreyas signing off. Hasta la vista.